while groups are presenting, please give them your undivided attention. Please do not play games on your iPads or on your phones or texting. You know, when you're up there, I'm sure you want people to pay attention to you. Everyone worked really hard on these presentations, so let's just be respectful and mindful and give everyone the attention that they deserve and respect that they deserve, okay? So we're about to get started, and great, I'll volunteer. If you guys are ready, you can go ahead.
All right, good morning, everybody.
Good morning.
Good morning. Let everybody sit down. All right, so we did current trend in physics 2. This is our second week of physics. And we have, I'm Cal.
Ever. Neil. Pablo. No, I'm kidding. Yeah.
And this is what we did.
So one of the activities we did was working with optics, so basically lens and everything. So go ahead.
All right, so we converging lens cases. In case 1, as you can see in the picture, the object is placed beyond the 2f, which is twice the focal length. The image is inverted and smaller than an object. Go into the page.
Oh, so the so this is the lens here, and the object is placed right here. So and the object is placed more than 2f, which is twice the focal length. And this is the image form when the light rays goes through the lens, and this is the object image form. It is inverted and is smaller. So, next one.
In case 2, the object was placed on f2, which resulted in the image forming the same size, the same distance, but inverted as the object.
So basically, on the second case, we had to put the object on as equal as the 2 focal length, and the image was, and the distance and everything was same, but it was just inverted. The orientation was just different.
In case 3, we had an object that was placed between 2f and f, and as you can see, it's right here. This resulted in an image form inverted, larger than the object and also further away.
In case 4, the image was placed on F, which resulted in the image not forming due to the light traveling parallel and not intersecting.
In case 5, the object was placed in between the lenses and the focus, which resulted in the image forming in front of the lens larger but the same orientation as the object. So this time, when it was placed after the focal length, the image was formed before the lens, and it was larger and in the same correct orientation. So this is how we tested all the cases with this machine. And then the image, this is where the spotlight was on the image, and this is the lens right here. And we had to see, and we had to test out all the cases. So the lens was placed either on F, the focal, or the double focal, and the object at the same place. So yeah. That's one of the activities we did. The second activity we did was mapping an electric field. This is the machine, well, this is similar to the machine what we use right here. And then what we have to do.
All right, an electric field surrounds any assemblage of charged objects. To determine the strength and direction of these fields, it is most convenient to first map the electric potential of the field, which can be measured with a voltmeter. From the potential field, the electric field can easily be determined.
In this lab, we have to map the electric and potential field resulting from 3 different configurations of charged electrons. So this is what we basically have to do. So the machine we had. So we had to put the plate down. So there were like 3 different plates we had to do. So this is what we did. We had to put it under the machine and tie it. And then we had to look individually for the zeros, and we had to put where the zeros were. So the zeros were the charges, basically. And then we had to map it. So in the end, it should have looked like something like this. And yeah, that's what we all have to do.
you the current trends in physics of what we did in our project. My name is Celine Jarrella.
Jennifer Garcia, Mayo Olivares.
Carlos Castro.
One of the things we learned about was our Archimedes principle, which is the buoyant force, which is equal to the weight of the fluid displaced.
Through this test, we submerged various materials in water, just plain H2O. These included wood, lead, and foam. One at a time, we submerged the objects and took down the information of what happened, exactly if it sunk or if it floated up or how much it weighed underwater. We found that blocks with less density would tend to float over the water. Blocks with more density in the water would sink to the bottom, and those with equal density to the water would float in between those 2 points. And this is the simulation. And this allowed us to test different cases. You could change up what material you're using to ice, brick, or anything, or choose any material, like putting the mass all the way down or the volume all the way up if you like. And you could also change the consistency and density of the water, which goes from air all the way to honey and an even denser object. It's pretty sweet, bro. Sometimes the simulation will break on you.
Okay, so the second lab we did, it was finding the density of objects. We had to find the density of brass, copper, and wood using the density of water and then calculate their specific gravity. First, we tied the object to a balance, measured and recorded the weights of the object in the air, then measured it in water, and then we used the appropriate equations to obtain the object's specific gravity. And then we calculated our percent.
This is the data table for the experiment, and the 2 objects that we decided to use were brass and copper. I was thinking of using something more heavier like Frank or something, but there was some issue about it not being legal, something like that. You know? Okay. So as you can see, the weight in water is less than the weight in air, and it's the same thing for the wood block. And after finding the weights, we calculated the specific gravity, which is the density of the object divided by the density of water. And right here is our results, which is the specific gravity of each of the elements. And this is our percent error, which is the margin between the expected value and the value that we got through the experiment. And for copper, we got 1.1%, and brass, we got 1.2%.
Another thing that we learned this week was elastic collisions. It has to do with momentum, and when we have like 2 objects colliding with each other. The definition of momentum is the mass times the velocity of an object. Mass in grams, to be kilograms, but it will have to measure the velocity centimeters per second. So one of the experiments that we did, we tested the principle of, or the law of conservation of momentum, that 2 objects are going to start with a certain momentum, and once they crash, the momentum is not lost, it is conserved, and it cannot be created either. So we have a constant amount of momentum before and after a collision. Here's an animation just showing as the objects approach each other and crash. We have a certain amount of momentum. Once they move away from each other, we still keep the same amount of momentum.
These are the equations that we used, and we had 2 different objects which had the same mass, but different velocities, and we have to match the equations so that they would be equal. So if our experiment was correct, the equations equations will equal to each other, which means that we did the project right, the experiment right.
Now we have a small video showing our actual experiment. We use two objects and we use this platform that resembles a hockey table with air to reduce friction and allow it to be completely elastic so the momentum would be completely transferred. This is what we did.
Each other, when they hit each other, they're gonna bounce. They're gonna bounce back. So I'm gonna put the box here, the other one with the needle here, and then I'm gonna give it a little push. Each other. They're gonna stick together.
Thank you guys. Thank you guys.
As we come to a conclusion, it would be wrong if we didn't say goodbye, like aspiring physicists should. And the way that us physicists do it is wait for it. We wait.
Thank you, Professor McCall. Thank you, Professor.
So again, this is another physics lesson. I'm Jackie Ferriola.
I'm Afia.
Michelle.
I'm Giselle.
Okay, so our first experiment was testing circular motion with a flying pig. And so as you can see here, these are some of the equations that we use where velocity equals circumference divided by time. Centripetal force is mass times centripetal acceleration, and centripetal acceleration is velocity squared divided by radius.
And those are pictures that show when during the process that we were doing. For this project, we had a flying pig with a string hanging from the ceiling. We had to measure the length of the string from the bottom to the bottom of the pig. We had to send the pig into a circular motion and measure the radius of the circle. We had to calculate the circumference of the pig's flying pattern. And we had to repeat the process for 3 times to have more accurate calculation. And then we had to find the percent error. This is a video of when we made the thing.
direction of a wavefront at an interface between two different media so that the wavefront returns into the medium from which it originated. Common examples include the reflection of light, sound, and water waves. Refraction is the change in direction of a wave due to a change in its transmission medium. Refraction is essentially a surface phenomenon. The phenomenon is mainly in governance to the law of conservation of energy and momentum.
And the picture shows the angle of refraction and what an angle of reflection looks like. So there's like two different things. There's one here and then here. Those are pictures of our job, which was the container containing water, and one needle was at 90 degrees, and the other one we were supposed to go on the desk sideways and look at what the angle of reflection was, and then we just wrote it down. That's it.
They can put their pen on
Okay, guys, please, thank you.
For this past 2 weeks, we had Professor Macayo, and we decided to create a small slideshow to show them our appreciation and just thank you for giving us the opportunity to learn so much about physics.
Oh my god.